Well, it is time for the invited talk. Our speaker is Zinan Wang. He is our program committee member and full professor at University of Electronics, Science and Technology of China, Chengdu, China. Talk topic is single-shot COTDR for distributed strain sensing.
Dear audience, my name is Zinan Wang from USTC, China. It is my great honor to make this presentation for OR2020, and I would like to thank the organizing committee for the kind invitation. Today, I will talk about a single-shot coherent OTDR for the purpose of distributed strain sensing. Here is the outline. At first, I will give a brief introduction to the background and motivation. Distributed optical fiber sensing systems have been widely used, and new application opportunities keep emerging. Among them, distributed strain sensing is an important member of this family. Here, I will give you three typical examples of their applications. The first one is to use DOFS to check vehicle by using fibers parallel to the tracks. The second one is for recording man-made seismic wave with borehole fibers. And third one is using the undersea telecom cables to monitor the natural seismic wave to study earthquake. As for meter-scale distributed strain sensing, here are three important parameters which define the practical value of the system. The first one is sensitivity, which is the minimal strain to be measured in that system. And the second one is slew rate, which is the measurable strain variation over unit time. And the third one is range, which is the distance between the interrogators and the farmost fiber end. All these three parameters matter. There are various methods to improve the key parameters. We start from the sensitivity. Firstly, we can use coherent detection to increase the sensitivity because the local oscillators can provide several orders of gain for enhancing the weak scattering signal. Secondly, we can use long chirp pulse and pulse compression because long chirp pulse can have large probe energy, and after pulse compression, we can achieve fine spatial resolution. Thirdly, we can use chirp pulse and cross-correlation in the time domain. In that case, we can have good noise resistance and fading-free operation. The second important parameter is sensing range. If the sensing range is extended by 25 kilometers, the radius scattering signal from the far end of the link will be reduced by 10 dB. One can use longer probe pulse to increase SNR, but it will lead to larger spatial resolution. And one can also use larger probe power to enhance SNR, but probe power is limited by nonlinear effects inside fibers. Luckily, there are other ways to solve the problem. The first one is use long chirp pulse. In that case, one can achieve 60 km sensing range with good SNR. And we can also use long chirp pulse plus distributed Raman amplifications. In that case, we have achieved 100 km single end distributed strain sensing. The third important parameter is slew rate. The definition is that strain slew rate equals the scan rate times the measurable strain change. In conventional phase demodulation OTDR, the maximum phase change is limited to 2 pi with unwrapping algorithm. The bandwidth of the probe pulse, which is bounded by the detector bandwidth, decides the spatial resolution, and the sensing range decides the scan rate. As a result, the strain slew rate of FiOTDR can be expressed as this equation. It should be noted that the noise is extremely harmful to the unwrapping process, resulting in severe distortion of the unwrapped signal. The The second case study is about coherent OTDR with cross-correlation. The strain slew rate of the COTDR can be expressed as this equation. If you sweep n times to complete one measurement, the receiver's bandwidth in a single measurement can be smaller than the frequency range of the reference pattern, so the measurable strain change can be significantly enlarged by sweeping multiple times. But f-scan can be small because of sweeping is usually time-consuming. So in a word, if we want to enlarge the slew rate, we have to achieve fast measurement speed. The best case scenario is to realize single-source measurement. At the same time, we can still enlarge slew rate by sweeping multiple times. Here I will introduce the principle of COTDR and how we achieve single-source measurement. Here is the general scheme of traditional COTDR. Probe pulses with different frequencies are used to generate different Rayleigh scattering traces. And after data processing, we can acquire the impulse response of the fiber under test, HFUT, which can be seen as invariant during one measurement period. And here we can see that the spatial resolution is defined by the pulse width. In traditional COTDR, although we can achieve high measurement accuracy, spatial resolution, sensing distance, and SNR are mutually restricted. Moreover, the sweeping process is time-consuming. Then we introduce pulse compression COTDR in order to break the trade-off among spatial resolution, sensing distance, and SNR. We can use long chirped pulse, and after match filtering, we get compressed pulse, and spatial resolution is inversely proportional to the bandwidth of the chirped pulse. So in the Rayleigh scattering pattern with pulse compression, spatial resolution is defined by the compressed pulse width. In that case, spatial resolution, sensitivity, sensing range can all be improved by a long chirp pulse, but the time-consuming sweeping process is still needed. Here we come to the most important part of this talk, how to realize single-shore measurement in COTDR. Here we look into the COTDR signal again. PT is a bandwidth limited signal, and it is a window signal P omega in frequency domain. The essence of sweeping process is to try to extract the information in different frequency component of HFUT omega, and larger extracted frequency range leads to finer spatial resolution. So let's summarize the difference here. For traditional COTDR, the chirp pulses with different frequencies are launched in order and finally get the HFUT. For single-shore COTDR, only a chirp pulse with large frequency range is used, but eventually it will acquire exactly the same frequency information. Here we name our approach as sub-chirp pulse extraction algorithm. We can call it SPA for short. The Rayleigh scattering signal of the whole chirp pulse can be expressed as S omega, and for sub-chirp pulse we name it as SM omega. It is the Rayleigh scattering signal with regard to sub-pulse PMT, which can be extracted from S omega, as long as the frequency range of PMT is within the frequency range of PT. We can construct the transformation matrix H omega, which links the complete pulse and the sub-pulses. Then we can get Rayleigh scattering signal matrix SMF, which equals S omega times the Hadamard product of matrix I and matrix H. Here is the flowchart of the data preparation. We do the data acquisition and get ST first. Then we do the Fourier transform to get S omega. Then we get the SMF. And then we do the inverse Fourier transform and get the absolute values. Then we can get the Rayleigh scattering patterns over frequency and distance. as shown in the top right figure here. In this scheme, signal-to-noise ratio can be increased by long sharp pulse and cross-correlation demodulation. Single-shot operation maximizes the scan rate, and the slew rate can be further increased by increasing the sweep range. In this session, I will demonstrate some experimental results. Here is the experimental setup. The sharp pulses are generated with an IQ modulator, and the coherent detection is used at the receiver side. There are 3 fiber lenses. The first one is 102 meters, and the second one is 50 kilometers, and the third one is 75 kilometers. And for all different cases, we use different pulse duration and pulse repetition rate. But we use the same chirp pulse range, which starts from 100 MHz and its bandwidth is 1 GHz. Duration of the sub-chirp pulse is 50 nanoseconds and the bandwidth is 50 MHz, and the frequency step is 4 MHz. The number of the sub-chirp pulses is 237. At first, we have to validate SPA, and this figure compares the SPA response with the traditional COTDR response. Essentially, they are consistent with each other. And in the short distance case, by looking at the non-disturbed area, we can see that the operation is fading free. And the sensitivity is calculated based on the noise flow of the string amplitude spectral density, which is about 2.3 picostring per square root hertz. We apply chirp disturbance to PZT, and we can see that the demodulated disturbance matches the excitation signal very well, and the main discordance comes from the resonance of the PZT. And we have compared the PZT response with the response shown in the PZT dataset. We can also see a very good match. Moreover, we can get very good linearity in terms of straight response. Next, we have tried long-distance cases. We can see that for both 50 kilometers and 75 kilometers, we can get a fading-free response and a very good signal-to-noise ratio. And finally, we can achieve 33 picostring per square root hertz at 50 kilometers and 94 picostring per square root hertz at 75 kilometers. Here are the conclusions. In this work, the essence of COTDR measurement is analyzed in frequency domain. So we can see that essentially COTDR is to extract the frequency domain information of the fiber transfer function. So based on this, we proposed single-shot COTDR scheme. As a result, we can achieve 2.3 picostring per square root hertz at 102 meters. Moreover, we can get very good sensitivity over 75 kilometers without distributed amplification. This scheme shows great potential for measuring large slew rate over very long range. Thank you very much for your attention. And here I would like to give you a list of our recent publications with regard to coherent OTDR. Thank you very much. Goodbye.
Do not hesitate to send your questions to OR2020@permc.ru. If we didn't ask your question online, please know that we have emailed this to speaker directly and immediately. Thank you.
The general sponsor of our conference is Macro Group company. Macro Group is a supplier of integrated solutions, equipment and components for phonetics, as well as a contract manufacturer and developer of electronics with 26 years of experience. The range of offered products includes both their own developments and equipment from the world-known manufacturers in the field of waveguide optics, lasers generation systems, spectroscopy, visualization, and photovoltaics.
Want to get the amplified spontaneous emission C-band source for free? Macrogroup invites participants to fill out a questionnaire before 2 p.m. plus 5 GMT on September 24th, following the link you have in the conference shadow or attached to this stream. On September 24th, Macrogroup will place the amplified spontaneous emission source of C-band by dense light semiconductors among the participants who have filled out the questionnaire. The draw will be randomized and the winner will be selected live. Using the contacts given by the participants in the questionnaire, Macrogroup will contact the winner to clarify the details of sending the prize. Thank you.
We thank today's home of our conference, Quantorium Photonics Scientific School in Perm. Dear colleagues, the next talk is called Creation of Fiber Tapes by Chemical Etching for Application in Fiber Sensors and Lasers. The full text in English and Russian is also available in Instruments and Experimental Techniques Journal.
I'm going to talk about formation of fiber tapes by chemical etching for application in fiber sensors and lasers. Usual design of a single-mode optical fiber avoids the influence of ambient condition on the electromagnetic condition propagation along the fiber core. This is possible because the evanescence mode field does not extend beyond the fiber cladding. However, for some applications, for example for fiber sensors or passive switches, for pulse fiber lasers, it may be useful to change the geometry of the fiber in such a way as to realize the possibility of interaction between the evanescence field of the core mode and the environment. One of the methods by which this interaction can be realized is thinning, or in other words steepening of the fiber, which can be embodied in two ways. The first method is the thermal stretching of the fiber, as a result of which the diameters of both the cladding and the core of fiber are reduced. The second method involves chemical thinning of the cladding. This approach preserves the geometry of the core as well as easier and does not require special expensive equipment. However, hydrofluoric acid, which is normally used for such purpose, is harmful to health. Therefore, we use a human-safe, aqueous solution of ammonium fluoride and sulfate. The length of tapes is regulated by the size of removed section of the fiber protecting polymer. At the first stage of etching, a fiber is fixed on a plank with a fluoroplastic tape and flooded with a volume of solution such that it covers completely the base segment. After thinning the fiber to a diameter of about 50 micrometers, the first stage of etching terminates. Next, the polymer cladding is removed on a length of 7 cm on both sides of the tape, which is flooded with a pool of the solution with a diameter of about 20 mm, and by changing the sign of inclination of the plank with an eccentric, which is fixed on a motor axle, the pool of solution moves to a distance of ± 2 cm from the center of the tape. A smooth transition from a cylindrical segment of the tape to the main fiber diameter is made with moving the solution. The transition of the tapered fiber was determined using the spectrometer with fiber-optic input. On this slide, we summarize the results of determining the optical losses at a wavelength of 1.56 micrometers in a series of tapers with different lengths and diameter from 5.7 to 24.1 micrometers. In tapers with diameters of more than 11 micrometers, the losses were lower than their detection threshold, which was equal to 0.1 decibel. The losses are considerable in taper with smaller diameters. In taper number 18, with a diameter of 5.7 micrometers, the loss was 1.9 decibel. A frequency reflectometer was used to scan a 4.1 mm long taper with a successfully decreasing diameter to determine the threshold diameter and spatial position of the losses. The threshold diameter after which the losses began to increase sharply was about 8.5 micrometers. The left peak corresponds to the position of the surface defects on the transition zone, which were formed at the solution-air interface, while the right peak corresponds to the end of the buried part of the fiber, and its high intensity indicates that a significant portion of radiation that propagates in the cladding is extracted to the environment there. The central peak corresponds to the losses which occurs in the area of cones and cylindrical part. To determine more accurately the sources of loss, we specially prepared taper with a 2 micrometers in homogeneity of the diameter of its cylindrical part at its average value of 8.1 micrometers, and after additional etching at 1 of 7.3 micrometers. From comparison of schematic image of tapered part of an optical fiber and the dependence of value of losses on the length of fiber, it is visible main location of losses. These are cones and defects on the cylindrical in transition parts of the taper. At the next step, we deposited on the surface of the tapered part of the fiber by the metal organic chemical vapor deposition or MOCVD methods either materials with properties of saturable absorbers or transparent and near-infrared area, such as bismuth telluride or zinc telluride respectively. For this purpose, we placed the fiber section about 15 cm in length with removed polymer coating, and the taper in the center in a tubular quartz MOCVD reactor, and hermetically sealed them there. The necessary precursor was applied by a high-purity hydrogen flow through the reactor, where they decompose under heating by a resistant furnace, and thin films were deposited on the surface of the optical fiber. During the deposition, we periodically recorded the transmission spectra of the fiber, with the tapered section in wavelength range from 1 to 1.65 micrometer. The possibility of using relatively large diameter from 16 to 30 micrometer tapers are lossy mode resonance sensors after coating them with zinc halcogenides is presented on this slide. To investigate the sensitivity of the fabricated sensors to the refractive index of the surrounding media, series of aqueous solutions of isopropyl alcohol were prepared. In this experiment, light from a halogen lamp was delivered to the spectrometer, passing through the sensors. The sensitivity of the reflectometer for first-order lossy mode resonance amounted to 5,100 nanometers per refractive index unit. Tapers with diameters smaller than 11 micrometers were used for manufacturing switches for pulse airborne fiber lasers. For this purpose, samples were deposited by a thin film of saturable absorber or filled with a mixture of silicon and a nanopower of a saturable absorber. For this purpose, thick film of appropriate materials were synthesized using the MOCVD method and were used as the initial materials for preparing the corresponding nanoparts. Nanoflakes that were removed mechanically from substrate were additionally ground in a mortar and mixed with a silicon in a proportion that provide a transmittance from 10 to 60% at 1.56 micrometers after being applied to the taper. The tapers were then integrated into the scheme of the ring fiber laser, whose circuit is shown in this slide. The generation of microsecond pulses was obtained on such materials as molybdenum diselenide, nickel oxide, and bismuth selenide that we tested at the saturable absorbers. The results of our work can be summarized in the following conclusions. Methods for forming fiber tapers by safe chemical etching for application in sensors and laser technologies has been demonstrated. In tapers with a diameter of the cylindrical region of less than 11 micrometers, the losses substantially increase when the diameter decreases and reach 2 decibels at a diameter of 5.7 micrometers. Using the frequency reflectometer, it was determined that main origins of the loss sources are taper cones. Lossy mode resonances arise in the transmission spectra of tapers with diameters from 16 to 30 micrometers after coating them with thin zinc selenide or zinc telluride layers. The prospect of using such lossy mode resonance sensors has been shown since the resonance position dramatically depends on the refractive index of the environment. Tapers with a diameter smaller than 11 micrometers were successfully used as the basis in production of switches for pulsed ring fiber array lasers. Our work was supported by Russian Foundation for Basic Research. Thank you for your attention.
Большое спасибо за ваш доклад. У нас есть два вопроса. Исследовали ли вы свои тейперы, уже готовые, на температурах? Было бы интересно и спектры посмотреть, и на той же Луне. Правильно ли коллеги понимают, что это OFDR, который вы использовали, он был от Lunar Technologies?
Да, правильно, но конкретно на этом приборе температурной зависимости не исследовалось, исследовались только температурные зависимости положения ЛМР резонансов в массивиде реакции после осаждения.
Понятно. Ну, в принципе, вы планируете паспортизовать температурное поведение уже готового тейпера потом, да?
Нас больше интересуют тейперы не в пассивном виде, то есть не чисто кварцевые, а именно как субстрат для осаждения тонких пленок или покрытия смесью полимер-нанопорошок и дальнейшем использованию этих конструкций либо в лазерах импульсных, либо в качестве датчиков. Вот именно с упором на эти два направления мы и исследовали изначально тейпера. То есть сами в целом пассивные тейпера без приложения к сенсорам или без приложения к лазерным технологиям нас интересовали меньше все же.
Понятно. Ну вот вы отчасти уже ответили и на второй вопрос. Звучит он так. Вы продемонстрировали ваши тейперы в волоконных лазерах, а удалось ли испытать их где-то еще? Ну, видимо, уже о каком-то законченном изделии речь.
Вот удалось испытать в качестве сенсоров для измерения показателей преломления водных растворов.
Понятно. Спасибо. Хорошо, благодарю за ответы на вопросы. Будем надеяться, что на следующей конференции мы уже услышим ваш доклад очно. Спасибо.
Да, я тоже на это надеюсь. Большое спасибо.
Okay, thank you so much, and it's great that we have some time for quick translation. The first question was: did you investigate your tapers for temperature behavior? How do they behave at some extreme temperatures using spectrometry or say OFDR used? We understood that it was from Lunar Technologies OFDR. And the answer was yes. This was OFDR from Luna, and but we didn't study the behavior at different temperatures. They didn't have such task. And the second question was, you have demonstrated your tapers in fiber-optic lasers. What applications are you planning for your tapers else? And the answer was yes, we have tested this in fiber laser, but the general application of TABR is as a sensor. And they tested this as a sensor too. Thank you. Let's continue. Do not hesitate to send your questions to OR2020@permsc.ru. If we didn't ask your question online, please know that we have emailed this to speaker directly and immediately. Thank you.
The conference thanks its publishing partner, Instruments and Experimental Techniques Journal. Here is the journal's general information. And the other journals supporting our conference are also presented here. Well, let us hear the next presentation, which is called Creation of Fiber, Topi's Biochemical Etching for Application in Fiber Sensors and Lasers. The full text in English and Russian is also available in Instruments and Experimental Techniques Journal.
Good afternoon. My name is Bochkova Sofia Dmitrievna. My report theme is the method for determining the impact location in a composite material using fiber-optical acoustic emission sensors. Often, composite materials are used as material structure elements. Their advantages are height strength, rigidity, wear, and corrosion resistance. The method proposed in this work can be used to solve problems in which composite materials constant monitoring is required. Such tasks include detection, estimation, and damage localization during the helicopter blades operation, wind generator blades, space satellite winds, parts the external train casing, and other objects. Thus, this work relevance is due to the need to monitor the characteristic durability of complex and heterogeneous structure during their life, to prevent emergency situations. To solve the problems, non-destructive acoustic methods are often used: ultrasonic method and acoustic emission method. To determine acoustic emission source location, the threshold detection method of the moment when an acoustic signal arrives at sensitive elements is usually used, TOR. This method works well for homogeneous materials where the acoustic wave propagation speed is approximately the same. However, in composite materials, the acoustic wave propagation speed can differ depending on the direction. This increases the calculation error. According to the considerate hour after work, the TOR method average absolute error is 200 mm. Another used method is AIC. This method is based on the Japanese scientist Hirosugu Akaigi information criteria. The method is based on comparing the noise factor and dunning the acoustic pulse and finding the functional minimum of its maximum difference for each grid point. The main disadvantage are the method and the need for the constant participation of a qualified operator, because the method involves manually determining the threshold value from launch to launch. In one of the studies required, the author automates this method and achieves good results with an average error of 3 mm. However, the complexity has only increased. In addition, piezoelectric sensor we used as sensitive elements in the experimental setup. These are due to some limitations in all system working, since such sensor require electric power supply. They are subjects to electromagnetic effects and often have large weight and size characteristics in comparison with fiber-optic sensors. Another interesting method is MAT. It is based on an estimation of the weighted median absolute deviation error. Localization method detects the impact by comparing its similarity to a pre-registered set reference signals. Fiber break grating, where the sensing elements in one of the experimental setup considerate of works with used MAT method. The authors have been obtained localization method MAT, average absolute error by 29 mm. The theoretical analysis of the most promising methods results in the idea of creating a more accurate and reliable source localization method for composite materials, where Fabry-Perot fiber interferometers were used as sensing elements. There are advantages with the exception of those traditional for fiber-optic sensors are their small size and high sensitivity. Composite graphite epoxy material was chosen due to its wide application in space and aircraft construction. The main purpose of this work was to develop a method for determining the impact's localization in a composite material using fiber-optic acoustic emission sensors and interferometric type. To achieve this purpose, the method was calibrated and tested on large amount of data received from a repeated source of acoustic signals. Complete list tasks required to achieve this goal is presented on slide 3. The primary concern was the mathematical expression derivation to determine the acoustic emission source localization. We have been obtained formulas for determining the absolute values of diagonals in relative quantitative terms, as well as final formulas for determining the coordinates of action. The position of the first sensor was taken as the origin. Where is the small letter d? Is relative values diagonals. Big letter D, absolute values diagonals. Letter N is side the sensitive plane. The next step was the algorithm model implementation using MATLAB software. We simulated the signal's relative arrival times to the sensitive elements depending on the impact source supposed location. Then the data using equations from previous slide. The relative modeling error, supposedly relied with the rounding operation use, was 0.05%. After that, the data have been obtained from the experimental setup, to be described on slide 7, and were fit into the model. Such data example is presented on slide 5. According to the order in which these signals from sensors were registered and the delayed relative magnitude to each other, The supposed impact coordinates were determined according to the formulas. However, this algorithm was not stable enough. Therefore, to increase the performance, an additional calibration algorithm was proposed. And also, empirically select the most optimal threshold values for each of the recorded signals, depending on the differences in sight distances. It identifies the sector in figure 4 from A to P, in which the impact is expected. Also, the most optimal for this experimental setup were the following threshold values. For the first recorded signals, 11 hundredths of a radian. For the second and third, 7 hundredths of a radian. And for the last, 5 hundredths of a radian. Thus, the problem of U-stability of the reference algorithm was solved. The experimental setup itself consists of 4 Fabry-Perot fiber-optic interferometric sensors, a composite graphite epoxy plate, 2 optical sources with a 1550 nanometers central wavelength, an analog to digital converter with a sampling rate of 1.2500 MHz, a programmable logic integrate circuit, and a steel ball weighing of 1.75 hundredths of a gram. This set, developed according to the proposed method, was experimentally investigated. A steel ball was used as an acoustic impact source. The ball fell from a height onto the sensitive composite plate that gave rise to elastic vibrations, which were recorded using fiber-optic interferometers set in plate into plate. The signals from the interferometers were demodulated using a layout acoustic emission signals recorder, in which the acoustic source localizations, energy, and duration were also calculated. After all the necessary calculations were complete, the result was displayed on the screen. The developed localization method, as well calculations of the pulse duration and energy, were implemented in the FPGA. The flowchart is shown on slide 8. In figure 6 on the left are the input signals, recording times of each sensor, control signal, reset signal, and clock frequency. And on the right output, source impact coordinates, as well as the duration and energy of the pulse. The block contains the main localization algorithm together with the calibration algorithm. In order to increase the input data repeatability, the acoustic source was the same for each test point. A total of 40 different points of impact were investigated. The real coordinates, the impact, are shown in green in figure 7, and the calculated coordinates are shown in red. The average relative localization error in the developed experimental setup was 4%. You can see all the results of the work we have done on slide 10. In the future, it is planned to improve the localization accuracy by modifying the exciting method. The method is supposed to be modified by introducing additional mathematical expressions, in particular outer and cross correlation algorithms, for more accurate determination of the acoustic signal arrival moments at the sensitive elements. Thank you for attention.
Так, большое спасибо за доклад. У нас есть несколько вопросов. Первый из них, раз конференция у нас с вами по оптической рефлектометрии, появляется вопрос, каковы преимущества вашей системы перед распределенными сенсорами?
Да, спасибо большое за вопрос. На наш взгляд, наша система подразумевает более дешевый вариант реализации, в принципе, оптической некоторой системы. Плюс она обладает быстродействием по сравнению с рефлектометрическими, например, системами. поскольку рефлектометрии есть зависимость от длины, быстродействие зависит от длины исследуемого участка, а у нас как бы нет. Вот. Плюс наша система обладает свойством надежности, то есть если у нас один датчик выйдет из строя, то есть возможность как бы продолжать сканирование оставшимися 3 датчиками. Вот. Нашу систему проще реализовать, то есть сложность гораздо меньше, чем в распределенных системах. Плюс еще у нас есть преимущество в том плане, что собрать под какую-то конкретную задачу, наверное, тоже будет проще. Вот, в принципе, наверное, на этом все.
Ну, исчерпывающе, спасибо. Еще один вопрос по поводу вашего заявления о том, что планируется улучшить точность. А каким образом это предлагается сделать?
Да, у нас точность просто, получается, зависит от порогов, алгоритмическая зависимость от пороговых значений. Вот сейчас у нас пороговые значения подбираются, можно сказать, один раз, вот, и для конкретного объекта. А мы хотим автоматизировать нашу систему, введя корреляционные алгоритмы. То есть они уже автоматически будут калиброваться под какой-либо исследуемый объект. Вот.
Понятно, спасибо. И вот у нас есть, успеваем еще один вопрос. А ведутся ли какие-то работы по коммерческому прототипированию устройства?
Наверное, честно будет ответить, что на данный момент нет.
Вы надеетесь на появление каких-нибудь инвесторов наверняка?
Да, мы надеемся, что мы автоматизируем систему, она будет гораздо более точная и, да, уже потом в поисках инвестора.
Хорошо. Спасибо за ваши ответы. Будем рады видеть на нашей конференции еще.
Спасибо большое.
Okay, I need to translate it again. The first question was about what is general. What are the general advantages of your system versus distributed systems? And the answer was it's much easier to implement. It works with more precise characteristics, and if something goes wrong with the single sensor, the other sensors work okay. And some other advantages. The second question was, you said that you are planning to increase the precision of characteristics of performance of your system. How do you plan to do this? And the answer was, we plan to work with the calibration coefficients to improve the software of data processing, and this is how they are going to increase the precision, the performance, to improve the performance of their system. And the third question was, are you about to make the commercial device? The answer was not yet. They waiting for the improvements of this device, and then maybe it could be possible. Thank you. Do not hesitate to send your questions to OR2020@permsc.ru. If we didn't ask your question online, please know that we have emailed this to speaker directly and immediately. Thank you.
Okay, the next presentation is called Improving the Accuracy Characteristics of a Fiber-optic Sonotone Streamer for Marine Geophysical Exploration and Seismic Exploration. The full text in English and Russian is also available in Instruments and Experimental Techniques journal.
Greetings, my dear colleagues. My name is Alexander Vlasov. I am research engineer from M.Yu University, St. Petersburg. First of all, I would like to extend my gratitude to the organizing committee of the conference for the opportunity to deliver my presentation. The topic of my research is improving the accuracy parameters of fiber-optic hydroacoustic towards streamer for marine geophysical and seismic surveys. Due to the strict time limits of the report, detailed information on the results of the study is presented as references to published works. Seismic streamers are usually used as an acoustic signal receivers for geophysical and seismic surveys. Historically, the geophysical market has been occupied by piezoelectric streamers, which have a number of fundamental drawbacks: low sensitivity, high tolling due to inverse piezoelectric effect, high cost, high weight and size parameters. Currently, M.Yu University has developed a fiber-optic streamer based on a system of fiber-optic interferometric phase sensors as a part of a grant. This solution has a number of advantages in comparison with classical approaches. Use the requirements for the coherence length and modulation rate of the interrogating optical source. The optical scheme or fiber optical streamer is constructed according to the principle of phase matching differential interferometry, for which a so-called compensation interferometer was included into the dry end part. You can see it here, compensation interferometer. However, for this work is the fact that this interferometer also has a sensitivity to external vibroacoustic impacts, which leads to the appearance of an uncorrelated with the signals from sensors component in the interference pulses. You can see it here. Of this problem is confirmed by, for example, the level of age and noise floor of the streamer increases up to 30 decibels when the cooling system of the unit is under operation. This frequency rate from 0 to 500 Hz is the exploration by seismic methods. Work, we carried out scientific and technical literature on the topic of fiber optic interferometric measurements under the environmental noise impact. Methods for reducing of unwanted acoustic sensitivity were classified in accordance with the complexity of their industrial implementation, from those that can only be used in the design of new measurement system to those that can be implemented at any stage of the life cycle of the measurement system and even in post-processing of obtained data. The task was set to prepare a number of technical solutions to reduce the undesirable acoustic phase sensitivity of the fiber optic interferometer and experimental studies of their effectiveness. Let's start with the results. In the course of this work, we developed an optical circuit that interrogate fiber optic interferometer as a sensor for vibroacoustic impacts on itself. It allows separately register the corresponding interference phase signal and subtract them individual signals for each pulses of sensitive elements and subtract them after the demodulation, and by this means to compensate the external influence. This is possible by implementing an additional optical source which operates in the continuous waves mode. By implementation, the principle of polarization division multiplexing. As you can see, polarization rotator rotates the polarization plane of additional source to the orthogonal stage to the first optical source. Then you register individual compensation phase signal for each sensor and just subtract them. The effectiveness of the proposed scheme was tested during the testing of fiber optic streamer. As it can be seen from these plots, its time domain, its frequency domain, the of a noise signal, which amplitude is 20 times larger than the hydroacoustic signal from sensors, which makes it possible to detect a formation signal and suppress the noise signal by more than 4 decibels. The signal to noise ratio at a frequency of 500 Hz thus increases by 14 decibels. The detailed information on the study is presented in part of this research is the study of the possibility of reducing the acoustic sensitivity of fiber optic components by the implementation of protective coatings. In the literature, this method was also mentioned. However, for the successful application of it, it requires the accuracy of applying galvanic and polymer coatings at the level of micrometer units, which is a relatively challenging protest task. Failure to do this will significantly increase the level of acoustic sensitivity. As a result, according to the literature review, by means of numerical simulation and three-dimensional plots, this plot describes the dependence of the acoustic sensitivity of fiber optic component, modulus, and Poisson's ratio of its coating. The study of this plot allowed us to conclude that coating samples, which have simultaneously high values of these parameters, are the effective ones. Since there is no isotropic construction material satisfying these conditions, more than 10 samples of fiber optic sensors with heterogeneous multi-component contents with a high compatibility with standard cabling technologies were prepared. This slide shows the result of an experimental study of the three most effective coatings. Maximum suppression of optical sensitivity at a level from 10 to 26 decibels in the frequency range from 20 to 5,000 Hz compared to an optical fiber in standard acrylate coating. The most effective coating turned out to be a telecommunication optical cable with steel rope armoring of fibers. The modulus of this construction is provided by steel, and Poisson's ratio is provided by its elastic properties as well as the presence of hydroacoustic in this construction. A description of an experimental setup, measurement techniques and procedures, and the full results of the study with discussions are presented in the referenced articles. Part of this study is the development and experimental testing of the effectiveness of the fiber optic case for protection against external vibration and acoustical impacts. As a result, methods for case acoustic conditioning and a steel spring-based protective suspension system were proposed. Constructions were designed to protect the interferometer from external air and structural acoustic waves. The structure of the proposed protective case is presented on this slide. The proposed technical solutions reduce acoustic noise impacts by up to 21 decibel in the frequency range from 20 to 1000 Hz, which is extremely important in geophysical studies. The main stages of the study and the results with discussions are presented in the referenced articles. Assembly of proposed passive technical solutions for protecting a fiber optic parameter was tested during field tests storing fiber optic streamer in open water in the Kola Bay. Based on the output of this test, the following results were obtained. The average level of aging noise of the fiber optic streamer external vibroacoustic influences was not more than 4 pascals per square root of hertz in the frequency range from 20 to 2000 hertz. At the same time, the signal level from the sensitive elements when towing the streamer is more than 30 decibels larger than the signal of the vibroacoustic impact on isolated compensation interferometer. Together, the source of geophysical signal, the so-called sparker, signal to noise ratio in the same frequency range was more than 18 decibels. The main stages and test results are presented in the articles referenced on the slide. So, in the course of this work, the review, analysis, and classification on optical noise desensitization methods were carried out. Fiber cancellation technique and optical circuit for its implementation was proposed. The achieved effectiveness of noise signal compensation was more than 24 decibels. The implementation of fiber sound protective coatings allowed us to achieve a decrease in sensitivity at the level from 10 to 26 decibels in the range from 20 to 5000 Hertz. The proposed protective case with vibroisolation suspension system allows to decrease phase acoustic sensitivity of fiber optic interferometer up to 21 decibel in the frequency range from 20 to 1000 Hertz. Proposed techniques were implemented in the geophysical streamer system and were investigated during in situ field test. This allowed to achieve an average agent noise floor of less than 4 millipascals per square root of hertz and average signal to noise ratio more than 18 decibels in the frequency range from 20 to 2000 hertz. In addition, obtained results are applicable for environmental noise protection of other types of fiber optic interferometers and other cavities. Thank you for your attention. I hope you enjoyed my presentation. Please feel free to ask any questions or to contact me using proposed links. Stay safe and have a nice day.
Так, большое спасибо за ваш доклад. У нас есть два вопроса. Вот. Ну, раз конференция у нас по оптической рефлектометрии, часто появляются такие вопросы. Какие вы видите преимущества квазираспределенной системы перед распределенной? Мы знаем, что гидрофоны бывают и чисто на принципе COTDR, и на каких-то других распределенных техниках. Вот что вы об этом можете сказать?
Я думаю, что для применения в гидроакустических геологоразведочных комплексах, соответственно, квазираспределенная система может теоретически обладать большими преимуществами, поскольку там более просто выявить конкретное расстояние между фазовыми центрами гидрофонов, а что может пригодиться при обработке именно сигнала с геологической точки зрения.
Ага, спасибо. Есть еще вот такой вопрос. Вы опрашиваете опорный интерференционный канал в вашей системе для устранения погрешности. А если вы извлекаете один датчик из сигнального канала, то вам что нужно сделать с опорным? Его нужно поменять или просто достаточно перекалибровать систему?
Данное применение, которое, соответственно, озвучено в докладе, позволяет компенсирующий сигнал для каждого из гидрофонов получать свой индивидуальный. То есть, соответственно, если по какой-то причине для одного гидрофона, соответственно, если один гидрофон вышел из строя или, как вы говорите, исключен, то для остальных их индивидуальные компенсирующие сигналы, они, собственно, остаются таковыми. То есть, что, с одной стороны, позволяет достичь наибольшей эффективности подавления и, соответственно, позволяет реконфигурировать, соответственно, систему под различные условия. Это достигается тем, что, как следует из доклада, опорный, соответственно, вот этот сигнал, он регистрируется при непрерывном излучении источника оптического излучения за номером 2, то есть интерференция в непрерывном режиме. Из вот этой всей непрерывной интерференции вырезаются по времени те кусочки, которые соответствуют сигналам от каждого из гидрофонов.
Понятно. Спасибо за исчерпывающий ответ. Будем рады видеть вас на нашей конференции, следующей конференции очно.
Большое спасибо, очень надеюсь, удастся посетить.
Well, again, it is very good that we have some time for the translation. The first question, a very popular question from the ones who prefer distributed systems. What advantages of quasi-distributed system you could mention? And the answer was for hydroacoustics and the geological studies, it is much easier to find the distance between the phase centers in hydrophone that could ease the data processing. And the second question was, you interrogate the reference channel as well. So if you exclude or change one of your sensors, does this mean that you need to recalibrate or even change the reference channel? And the answer was exact application allows to obtain the individual calibration signal for each sensor. So if it is removed or even changed, it's not a problem for such a system. Thank you. Let's continue.
We are in air. Dear friends, colleagues, participants, I'm glad to welcome everyone. And now we're starting a joint section of Russian fiber laser seminars and international conference on optical reflectometry, sensing and metrology. There are two different events, conferences. The first one in Novosibirsk, the second one in Perm, but having many common topics. This section is finish line of these events, and I should remind you that this event broadcast to YouTube channel, and the first speaker of our session is invited speaker Andrei Fotiadi. Andrei, are you hear me? Andrei?
Yeah, I'm here. Yeah, I'm here.
Oh, hi, Andrei.
Yeah, hello.
Oh, please, you may present your topic.
Окей. Я по-русски буду говорить, да? Это можно ведь?
Andrei, I know that several participants say in English only. I see that.
Indeed. Ваня, у меня предзаписано все. Как надо сделать? Я тогда могу свой звук выключить тогда, или как надо сделать, скажи мне.
I think that in English is better.
But my slides are in Russian, so it is okay. I will try to do something, but it's Okay, so but in this case I have to switch off my sound from the computer, I think.
Okay.
Так. Ваня, а как выключить компьютер, звук? Иначе меня будет говорить эта штука все время по-русски.
Андрей, в первую очередь вам необходимо, когда вы расшаривали экран, не ставить галочку «Транслировать звук с моего компьютера». Это в первую очередь. Во вторую очередь вам необходимо будет выключить звук на самом компьютере. Для этого, ну, если у вас там колонки, можете их рукой подрегулировать.
Я выключил уже есть готово. Выключил на компьютере. Нет, как я вас не слышу тогда?
Ну, в общем, вы начнете говорить и по-английски, и нас не нужно будет слышать, когда вы закончите. Мы...
Хорошо, ладно, я понял. Хорошо, так, значит,
надо
сделать...
трансляции, нам напомню еще раз, галочку «Транслировать звук» не ставите левый.
Я попробую сейчас. Значит, убрал галочку.
Просто, Андрей, я вижу, что есть два англоязычных слушателя из Китая.
Слушай, да.
Еще у нас
сказали, это
есть английский стрим.
Окей, у меня все слайды по-русски, Вань. Хорошо.
Я думаю, ничего страшного. Okay. We can.
Okay, I will try. So, ты видишь мои слайды, да, сейчас?
Yep.
Так, слайд-шоу.
From beginning.
From beginning, окей. Так, блин. Надо теперь это все выключить. Okay. Can you see me, no?
Yes, sir. Yes, we see it. Okay. You may start.
Так. Меня слышно вообще было или нет?
Все хорошо, вас слышно.
Да, но дело в том, что мне переключают слайды из-за того, что у меня там стоит этот звук теперь. Я должен убрать все тогда эти вот... Окей, ладно, я буду пытаться. Окей. So, hello, everybody. So, I'm very glad to be here in Novosibirsk, practically. So, I would like to present some talk on distributed measurements of the vibration spectrum with coherent reflectometry, employing self-injection locked semiconductor laser as a master oscillator. So, the matter of the talk is that we prefer to use very simple solutions for laser instead of commercial lasers commonly used with coherent reflectometers. So this is headline of my talk. Okay, it's in the next slide. Okay, this is headline of my talk. And here is okay. So I will miss this one because it's not so interesting for English people, but Russian people can read this one. And so, this one is a configuration of the narrowband laser based on injection locking mechanism. So, the simplest way to have narrow line width of semiconductor laser is to use a self-injection locking mechanism. In order to do this, you need to combine your laser with some fiber components. It's a very standard fiber components like two couplers and one circulator. And in this case, the laser radiation is passed through the circulator and introduced to very high quality, high ring cavity, and pass through this cavity and return back into the laser. And so, as a result, the resonance frequency of the cavity becomes the working frequency of the laser operation. So it's a very simple way to have very narrow band laser. However, its behavior is not very stable. because it's influenced by many environment noise, and it's influenced mainly by temperature fluctuations, which affect the length of the ring cavity. And so the laser frequency follows the ring cavity resonance, and so it's introduced some perturbation to the laser. So this perturbation can be seen in this slide. So you can see two oscilloscope traces, which obtain typical oscilloscope traces, which has been obtained from the laser cavity, ring cavity to outputs. One output is a resonance radiation, which is radiation which is amplified by the ring, so which is collected by the ring. And the second output is non-resonance radiation. Non-resonance radiation is the radiation which is reflected by the ring, not accepted by the ring. And so when resonance, so both these signals are fluctuated, and so when resonance radiation is increased, the laser became working in injection lock regime. And so more this resonance laser output, this high increase of the resonance radiation corresponds to the narrowing of the laser spectrum. And opposite, when the resonance radiation decreases, the line width is increased. So you can see two limit laser line widths, which are 3 kilohertz in the case of narrow band the narrowest band radiation. Sorry. And the line with 22 kilohertz is broadest. And so when laser line became broader, it's possible to have more scoping events. And this more scoping events makes laser operation very unstable. However, what is important point is that the laser works in the self-injection loading regime between the Moscoping events for a longer time than Moscoping events occurs. And so the stable laser operation is about 97% of all watching time, and only 3% correspond to the Moscoping events. So in this situation, the laser can be used as a master oscillator for coherent reflectometry, because it's coherent reflectometry applications like vibration sensors or acoustic sensors. It is not so important to monitor everything all time. So, and percentage of perfectly working time, 97% is okay for coherent reflectometry. So this is our proposal and what we are trying to do is just to demonstrate that that very simple configuration working well with coherent reflectivity and can be replaced commercial device. So this is very simple our setup. We have our laser and then erbium amplifier, bandpass filter, electro-optical modulator, which produced 100 nanosecond pulses with 2 kilohertz repetition rate. And that these pulses are introduced into the fiber. The total length of the fiber is 10 kilometers. And at the point of 9,270 meters, the laser, the fiber is affected by the acoustic waves introduced by the loudspeaker. And so in this situation, we have this setup allows to measure this vibration through the accepting the light, ray scattering light, which relay scattering light, which is collected and detected by the fast detector. So in this situation, we have we have data traces, many data traces like reflectograms, which is consequence. This consequence of these reflectograms constitute a matrix where the one dimension is gives coordinates along the fiber, and another dimension gives time coordinate along the time. And so then what we are doing is we average, sorry, we average. So first, what we are doing with this signal is first we make averaging along the coordinate of fiber. So and normally there is some window is which length is W, and so this length is much narrow, normally narrow than the resolution, special resolution of the sensors associated with the length of the pulse. And so in this situation, so we accumulate the signal. It allows us to decrease the noise. So next thing is so finally, so we make many this matrix is transduced to the matrix which averaged along the coordinate axis, and then we have matrix like this, which can be used for further processing. So next things what we are doing is we averaged consequence element in time domain now, and so we used n elements consequence element in this dimension, and then averaged it and forming this matrix where G is the number of this averaging number, and the M is a delay. Sorry, is a delay between two consequence averaging procedures. So factually, N and M became two important parameters for the processing algorithm. And here we compare the traces and information obtained through the sensors in the case and compare to averaging procedures. And in the first case, we use normal procedure when we have M equal 1, and the second case we have M equal 20, and so you can see that in second case you can recognize the signal which appears in at 9 kilometers and 9 kilometers 700 meters. So it's exactly what we where we apply our vibration. So this slide gives comparison of two lasers, our laser and commercial laser, applied to used with this configuration. Sorry, it's automatically. Okay, so we have two lasers, and so you can see that two pictures obtained nearly the same. It's no significant difference. Even ours is better. So next one is this is a second experiment, and so in this experiment we have compared our laser with another commercial laser. And so in this case, we have the same setup, but the length of the fiber was 4.5 kilometers. And so we used two things in order to stimulate vibration. It's a shaker, which was working at 850 Hz, and a stretcher, which was working at 3 kilohertz. And so now we compare performance of the coherent reflectometer with obtained with both lasers. So the signal processing procedure is nearly the same. So we again form the matrix, providing averaging through the windows in coordinate axis, and then after that. We can obtain this signal. It is just averaging, no more. This signal, which is, you can see here that our signal is 1.4 times higher than noise level. And then we can continue proceeding the signals and making averaging, we discussed before, it's averaging in time domain. And so we have a set of signals like this. And can after that we can optimize parameters M and N in this processing algorithm in order to get maximum signal. You can see this can be achieved for the signal 890 Hz at point 890 meters. We got these numbers which maximally this provides about maximal high signal noise ratio. So then we optimized again using these values. We optimized the windows in spatial coordinate, and so we got again new number which corresponds to the maximum signal. In this case, signal noise ratio is 13.8 dB. Then, this is compares the result of the optimal data processing. And on the left, we have original data, and on the right, you have that the signal noise ratio in 3.5 times higher than in original data. So we have increased the signal noise ratio using using the processing of the signal. So this compares the signal obtained at frequency 850 Hz in point 890 meters for our laser and commercial laser. You can see that in our case, our laser works better than the commercial laser in this case. And here the same, but for another point, 3 kilohertz at point 2.5 kilometers. You can see that our laser works a little bit worse than the commercial laser, but difference is not so significant. So next point is so at this both signals are applied simultaneously, and again you can see the comparison. The performance is near the same, but okay, our laser is a little bit worse. But if you take into account the price of the laser, so this 1 dB difference is nothing. Here our third experiment where we used our setup and used our laser in order to measure the frequency of the vibration. So the vibration have been applied in the point 3.5 meters, so 3.5 kilometers, and the vibration frequency had been changed from 300 Hz to 5,600 Hz. So. And then, so practically set up the same, and again, we compare performance of our laser with performance of commercial laser. And so here you can see, so it is again the same pictures as before, but it is related to the new setup. You can see this signal noise ratio. In our case, and in the case of using commercial laser, nearly the same, ours only 1 dB less than commercial laser. So here again, in order to so here we have no new task. We have task now to measure the frequency of vibration. And so in order to take this signal, what we did is we again use reflectogram, then again averaged along the spatial coordinate, and after that immediately take Fourier transform in order to know distribution of the resonance frequency for each fiber points. Here, signal was applied 350 Hz, and you see here at the point 3.5 kilometers. And so here you can see that our laser works worse, but only 2 dB, and you can see that we have longer or higher noise level here. And so next point, it is 500 Hz. In this case, our laser works better, but again, the difference is not very high. Next point is 1.2 kilohertz. And so again, our laser better. So it's not worse than our laser. So it is a very simple solution, but much better than no big difference between them, both performance. Here, signal 3.7 kilohertz, and we have different, you can see difference 3 dB only. And again, at the last point, 5.6 kilohertz. It's again not big difference. So this summarizing is here as the frequency characteristic, amplitude frequency characteristics of the our device in both cases. You can see that okay, this line is a little bit lower than this line, but the difference very small. You can see that our laser works in the case of low frequencies. It can be associated with the frequency drift in our laser, which is about 10 megahertz per minute, and it is much greater than the frequency drift in the commercial laser, which is less than 1 megahertz per minute. And okay, and we have a low as well in at high frequency, a low signal noise ratio at high frequency. It associated with I think that it is associated with the fact that we have wider laser linewidth, because laser linewidth, our laser linewidth is about 5 kilohertz in this case, and the laser linewidth of commercial laser is about 300 hertz. So I said, but in intermediate points, both lasers gives the same performance. So, okay, so this is my slides associated with the same laser. It's just to discuss how to improve the laser performance, because in our experiment we essentially used laser which were not stabilized, because idea was to have very simple and very low cost solution. And so, okay, stabilization of the laser became more expensive, but in our case, in order to stabilize the laser, we used very simple solution as well, using the very cheap USB controller, in order to working with operation rate about 150 Hz only. And so it was enough in order to stabilize the laser near injection locking regime. Because the idea is for this feedback loop is just to support this regime, to keep this regime, because main line is narrowing and laser stabilization occurs due to injection locking mechanism, which is physical mechanism. It's not associated with feedback loop, but feedback loop was introduced just in order to keep this regime, no more. And so this is, allows to have very simple solution for this feedback loop. But additional benefit of the feedback loop is the possibility to control the linewidth, not only on the minimum level, but we can control the laser linewidth between 2.5 and 14 kilohertz as well, using different parameters for feedback loop. And so just additional things. It is a phase noise, which is change from the different points related to different laser linewidth. So the nearest laser linewidth 2.8 kilohertz correspond to the lowest curve, and this is correspond to the 14 kilohertz. And so you can see that the phase noise is the main contribution to the laser linewidth in our system. So this is amplitude noise, which is below than 130 dB per hertz. So it's not bad performance for the laser. So this is my final slide, and here I just tell that we used very simple solution in order to be employed with coherent reflectometry instead of regular commercial lasers used for this purpose. So one disadvantage of this configuration as well is the possibility to generate Boolean scattering simultaneously with the pump. And so laser is able to generate two wavelengths, and so this laser can be applied for Boolean analyzers and Boolean reflectometry. Sorry. And what is important, so we start this work, and so we have some experiments, but I will tell about this next time. Thank you very much for your attention. Thank you. And
thank you, Andrei. Any questions, please? For questions, please raise your hand or
Sorry, sorry, it's okay now?
It's okay, I see you.
Okay, no, I switch on the audio, so it's no.
Or you can put your questions to the chat.
Okay.
Okay, could I ask, Andrei, do you plan to commercialize your laser and your sensor system?
So it would be interesting, but so in this case we need to work together, I think.
Sorry, what?
I think in this case you need to help with commercialization, I think. So this.
Okay.
No, in fact, of course, it would be interesting because so normally a very simple setup can be used in order to have the same things what normal and commercial setups allows. And so I think for many applications which not require very strong, very precise measurements, very simple, very cheap solution can be used. So this is important. I think there is innovation aspects in this, yeah.
Okay. Any questions, please? No questions? Okay. Thanks, Andrei, very much.
Thank you.
Okay, the next speaker is Vladimir Burdin from Samara. Владимир.
Звук. Вы меня не слышите, звук надо включить.
I hear you.
Вы меня слышите?
Yes, yes. Да.
Я... Так. Приношу свои извинения, но как-то я не рассчитывал делать доклад на английском языке, поэтому не успел переключиться. Прошу прощения, буду на русском. Можно?
У нас нет выбора.
Вот, к сожалению, так. Ну, значит, мой доклад посвящен
Dear participants, Professor Burdin, his talk was in Russian, unfortunately. Okay. Можете продолжать.
Доклад посвящен достаточно узкой теме. Значит, обработка поляризационных характеристик обратного рассеяния на основе разложения прони. Ну, известно, что в кабеле существует избыточная длина, и параметры вот избыточной длины используются для ряда оценок. В частности, нередко параметры избыточной длины в кабеле рекомендуются в качестве комплексной оценки качества кабельного изделия. Радиусы изгиба волокна, распределение радиуса изгиба волокна в кабеле представляет интерес с точки зрения оценивания напряжения на изгибах, что необходимо для прогноза срока службы кабелей. И для маломодовых оптических волокон измерение кривизны позволяет оценивать коэффициенты связи мод. Ну, практический интерес представляет не абсолютное значение избыточной длины, а распределение этой длины по длине кабеля, то есть степень равномерности распределения по длине кабеля. Ну, естественно, для измерения этих распределений используются рефлектометрические методы. Ну, общее несколько, так сказать, формул по оценке избыточной длины. Предполагается, что избыточная длина волокно расположена внутри кабеля по геликоиду, и тогда, значит, избыточная длина связана с параметрами этого геликоида вот по таким формулкам. Ну и то же самое представлено еще ряд формул радиуса изгиба, связаны как с избыточной длиной. Ну, рефлектометрические методы измерения избыточной длины могут оцениваться либо по изменению затухания, если это волокна G652, но, к сожалению, для волокон G657 такие методы уже не пригодны. Методы маломодовой рефлектометрии, методы поляризационной рефлектометрии. Ну, на данном слайде представлено связь длины биения оптического волокна кабеля и его избыточной длины. Ну, то есть если у нас есть кабель, для которого избыточная длина известна, или же если мы измеряем избыточную длину кабеля при разных условиях, когда изменяется, эта избыточная длина изменяется, то можно определить избыточную длину кабеля в новых условиях. Ну вот, был предложен способ определения измерения длины биений в кабеле, где избыточная длина определялась вот по такой формуле. Для определения, собственно говоря, когда мы измерили поляризационные характеристики обратного рассеяния, чтобы рассчитать избыточную длину, применяются полариметрические методы. Наиболее широко применяется метод LCR, Level Cross Ratio, и методы на основе преобразования Фурье. Ну вот мы попробовали применить для этих целей метод на основе разложения Прони. Разложение Прони. Значит, разложение Прони основано на применении комплексных экспонент и затухающих синусоид. Ну, формула разложения представлена на слайде. Значит, в общем-то, все разложение, каждая составляющая описывается 4 параметрами. Чем хорошо разложение Прони? Модель универсальна. Она позволяет описывать как постоянную, так и экспоненциальную составляющую, чистый тон, убывающий, нарастающий комбинацию. То есть любую комбинацию сигнала достаточно точно она описывает. Плюс, по сравнению с преобразованием Фурье, если для Фурье мы должны рассматривать, так сказать, разложение от бесконечности до бесконечности, от минус бесконечности до плюс бесконечности, то есть, в принципе, бесконечное число несущих, то метод Прони ограничивает, существенно ограничивает число компонент. Ну вот, допустим, мы для того, чтобы получить погрешность порядка 0,01%, использовали не более 40 компонентов. Ну и кроме того, метод Прони обладает следующими преимуществами. Во-первых, отсутствует принципиальное ограничение на разрешение по частоте. Он подходит для анализа коротких сигналов с высоким коэффициентом затухания и позволяет существенно снизить погрешность оценок значений частот, которые присутствуют в сигнале. Ну вот что, собственно говоря, важно при обработке поляризационных характеристик. Ну, в данном случае, значит, в качестве целевой функции был метод наименьших квадратов рассмотрен. Для расчета коэффициентов разложения мы использовали известные алгоритмы, и число членов разложения выбирали так, чтобы погрешность аппроксимации не превышала 0,01%. Ну, алгоритмы, я не буду о них рассказывать, здесь изложены вот в приведенной литературе. Каким образом обрабатывали, собственно, поляризационную характеристику? Ну, предварительно саму характеристику сглаживали с помощью сплайнов. На сглаженной характеристике методом скользящего окна выделяли участок, который обрабатывали. Для выделенного участка находили параметр разложения Прони и оценивали погрешность аппроксимации. Если она удовлетворяла, значит, переходили к следующему шагу. Выделяли доминантные частоты и вычисляли средневзвешенное значение частоты на выделенном участке. После этого определяли длину биений для выделенного участка, рассчитывали оценку длины биений на участке по формуле и затем рассчитывали, собственно говоря, длину биений. Ну, для того, чтобы протестировать наш метод, мы использовали следующую методику. Мы учитывали, что длина биений прямо пропорциональна изменению температуры. То есть при понижении температуры избыточная длина волокна в кабеле должна пропорционально температуре увеличиться. И, собственно говоря, значит, если мы измерим зависимость температурной избыточной длины в кабеле и построим ее линейную аппроксимацию, то есть погрешность этой аппроксимации мы принимали за погрешность нашей обработки. Ну, для измерений, значит, в климатическую камеру помещался барабан с кабелем. На конце барабана все волокна зашлифовывались в муфте. Значит, осуществлялось 3 цикла температурных. Значит, на каждом цикле температура последовательно опускалась до минус 30, минус 40, минус 50 и минус 60 градусов. Например, характеристик при температуре плюс 70 и минус 60 градусов представлен на слайде. Здесь представлены характеристики, пример характеристик для одного из волокон для минус 30, минус 40, минус 50 и минус 60 градусов Цельсия. Ну вот, собственно говоря, классический пример результатов характеристик. В 80% случаев мы получали, ну, примерно вот такие характеристики. То есть, как видим, достаточно хорошая линейная аппроксимация получали в пределах, значит, 5-10%. Ну и заключение. В целом результаты тестирования позволили говорить о возможностях применения предложенного алгоритма для обработки на основании разложения брони. Однако, значит, и действительно, при сравнении с методом ЛСР мы получили несколько лучшие результаты, но для того, чтобы говорить что-то определенное, надо, конечно же, иметь значительно больший объем статистических данных тестирования. То есть пока мы можем говорить, что брони не хуже известных методов. Ну а вот наличие отдельных примеров с недопустимо большой погрешностью, то есть у нас где-то 80%, все это было очень замечательно, 5-10% погрешность, а вот где-то примерно 15-20% от общего числа рефлектограмм, ну, погрешность очень большая была, то есть совсем, как говорится, отлично от линейной, но это как раз подтверждает необходимость, что при измерении длины биений по поляризационным характеристикам, ну, недостаточно измерять, собственно говоря, при одной поляризации, надо, ну, снимать серию характеристик при разных значениях состояния поляризации. Ну, у меня все. Спасибо за внимание.
Спасибо. Доклад, вопросы, пожалуйста, в чат или поднимайте руки. Ну, я хотел спросить вопрос, я не очень просто понял. Вот 80% реализации успешные, то есть это просто разные рефлектограммы были, разные реализации?
Да.
Разные... Волокно было одно? То есть, как бы...
Нет. Это кабель у нас был 16-волоконный кабель. И, значит, как сказать... 16, ну, вы правильно сказали, 16 волокон, и плюс к 16 волокнам, и каждое волокно снималось неоднократно.
Ну, то есть это 80% среди всех измерений, да?
Да. Ну, можно считать, что из 16 волокон для, так сказать, для 3 волокон мы выпадали из результата измерений.
Спасибо. Еще вопросы, Аleinik? Вопросов не вижу. Давайте тогда поблагодарим. Спасибо.
Так.
Да. And the next talk from our colleagues from China, and as I understand, the first speaker is Professor Huang. Yes.
Hello, everyone. Can you hear me?
Yeah.
Yeah, okay. Thank you. Good afternoon, everyone.
Please full screen. Yes, okay.
Yes, my name is Wenju Huang from Institute of Semiconductors, Chinese Academy of Sciences. Today, I would like to introduce some of my progress about the results on temperature, composition of ultra-high resolution FPG static strain sensors in cluster deformation observation. This is outline. I will give you background principle, sensor design, field tree, and discussion and conclusion. Now I will introduce background first. Nowadays, for every country, earthquake monitoring is important because it is the most serious disaster. The change of cluster strain state is the most direct reason of earthquake and one of the main methods for earthquake prescription observation. When earthquake is coming, the strain state of the earthquake deformation will be changing, but its amplitude is small, about nanostrain. The frequency is also low, below 1 day. So, in general, high resolution static strain is measurement for calculating the local earth crystal deformation. In the past, electronic extensometer is widely used for crystal deformation observation. It has a very high static strain of resolution, about 0.1 nanostrain, but it has extremely large size and poor environmental flexibility, such as electromagnetic interference, air pressure, and lightning. Recently, FPGs is used for crystal deformation observation. It has many advantages, such as high resolution, small size, lower transmission distance, and good environmental flexibility. However, for FPG sensors, the cross effect of strength and temperature is an important issue. Usually, reference FPG is used for temperature composition. For nano strain level sensing, the accuracy of temperature composition determines the static strain resolution and the long-term drift of the system. But in particle applications, due to the temperature sensitivity difference between the sensing FPG and the reference FPG, the measurement system will have a large long-term drift, which will also affect the static measurement resolution of the system when the amplitude temperature fluctuates. Next, I will introduce you the principle. We use FPG-FP as sensing element. A narrow line-wise tunable laser is used for integrating the wavelengths of the FPG-FP. A sensing FPG-FP is used for strain sensing. Reference FPG is used for temperature sensing and then used for temperature composition. For FPG-FP, the FSR is related to strain and temperature. We can realize strain and temperature sensing by measuring the FSR. We use phase mark technique to write FPG-FP. The FSR is about 4 picometer and the otherwise is about 0.01 picometer. This is the diagram and the picture of the design FPG-FP strain meter. The sensing FPG is fixed directly with backblock for strain transferring. Reference FPG is placed closely to keep the same environmental temperature for high resolution temperature sensing and the temperature composition. Temperature sensing FPG-FP is fixed on the stainless steel material to increase the temperature sensitivity. The sensitivity of the FPG-FP temperature sensor is about 19.96. Now it is the past of field tree and discussion. The field tree is carried out in Jinzhai Seismic Station, Anhui Province, China. The FPGFP strain meter and the temperature sensor is in the cave. The integration system is in the earthquake observation room. As a test results, the wavelength noise level is better than 0.001 picometer. First, a field test shows that the sensing system can record the slight temperature disturbance in the cave with 0.2 resolution. Second, oscillator signal can be also recorded by the FPGA strength meter. And the resolution is about 1.45 nanometer strain compared with the result of the electrical extensor meter and the serial child. There is no long-term drift of the results recorded by FPGA-FP. Finally, earthquake from up to 8,000 kilometers away is also recorded. In the end, we make a conclusion. We propose a high resolution strain and temperature sensing technique by measuring the FSR of two FPGA-FP, which can improve the static strain measurement resolution and reduce the long-term drift of the system. Field test shows that a temperature compensation of 0 to 0.2 and a static strain measurement resolution of 1 to 1.45 can be achieved. The experimental results suggest that the appropriate sensors have an ability to record the tide signal, distance earthquake, and ambient temperature with a higher signal noise ratio. Thank you for your attention.
Thank you. Any questions, please? Put your hands or raise your hands or put questions to the chat. Okay, I have a question. Could you compare your FPG sensors with other strain sensors? Better or not?
Sorry, I can't hear you.
Could you compare your sensor with other strain sensor?
Yes. This picture, we can look at this picture. The black line is the FPG strain meter, and the red line is the electric extensor meter. They have a same trait.
And what sensor is better?
Hello?
No. Okay, thank you. Any questions? Okay. No more questions. Thank you very much. And the last speaker, Professor Zhang.
I'm here.
Yes. Yes.
Can you hear me?
Yes.
Okay. Okay. Thank you.
We see your presentation. Please make a full screen.
Okay. Okay. Thank you. I'm Zhang Jianxiang from the Institute of Semiconductors, Chinese Academy of Science. It is my great pleasure to be here to introduce our latest research results to you. My topic is field test of the board fiber-optic interferometric seismometer, which modulation depth feedback control. Nowadays, fiber-optic seismometers are widely used in oil and gas resource exploration and seismic monitoring. Because of its ability to extra environmental resistance and large-scale capabilities, many oil and gas exploration companies have issued interferometric fiber-optic seismometers. For example, Optical, PGS, Paulson, and Magica. However, many factors limit the application of fiber-optic seismometers in this field. Firstly, due to the limit of noise of the system light source, it is very difficult to realize a high resolution within a wide frequency range for the interferometric fiber-optic sensing system, especially below 1 Hz. Unfortunately, in the field of seismic monitoring, the measured signals often have a very wide frequency range and have very rich information below 1 Hz. Secondly, modulation depth and carrier phase delay limit multi-channel consistency and stability. The modulation depth of the multi-channel optical fiber seismometers should be controlled as fixed value and the phase delay as 0. Otherwise, amplitude, stability, and channel consistency will be very poor. Aiming at above problems, our group researched the broadband fiber-optic seismometer. In order to achieve multi-channel high resolution with a wide frequency range, I did 3 things: reduce the low frequency noises, optimize the optical fiber seismometer, and improve multi-channel consistency and stability. At first, we have designed fiber-optic seismometers based on Michelson interferometer and fiber-optic seismometer array, which frequency range reached below 1 Hz to 500 Hz. Sensitivity reached 41 dB. Secondly, the laser source is locked to an absolute frequency referencing using PDS technique to reduce the low frequency noise level of the laser source, which can optimize the low frequency performance of the system. Last but not the least, modulation depth and carrier phase delay feedback control is realized by time division locking technology. The basic principle of the post technique is shown below. We divide the system into 4 modules: fiber optic interrogation and photoelectric detection module, algorithm module, analog to digital converter module, and digital to analog converter module. The core idea of this technology is to make the phase measurement of each channel a closed-loop system according to time division, and realize the feedback local of carrier modulation depths and carrier phase delay one by one. A direct digital is used to generate carrier signals with different amplitudes and initial phase for the fiber optic seismometer array. The carrier modulation depth and carrier phase delay of each channel seismometer can be controlled to be 2.63 and 0 by changing the amplitudes and the initial phase of DDS. Then the interference fringes of this channel are controlled one by one. A phase measurement sequence is recognized by PGC acting demodulation algorithm. In this process, the carrier modulation depth and the carrier phase delay of each channel are efficiently controlled by real-time feedback and are not affected by the external environment, which is conducive to improve the consistency and stability between each channel. In order to measure the noise level of multi-channel fiber optic seismometers, we placed the fiber optic seismometers in a quiet and vibration isolated environment. A 1 Hz high-pass filter is used to eliminate low-frequency noise effects. The noise level of multi-channel interrogator is shown below. We can find that the noise levels of 3 selected channels are in good agreement with a level of about 118 dB. The fiber optic seismometers have the sensitivity of 40 dB. To further test the consistency and the long-term stability between channels of a multi-channel interrogator, the background noise level of all channels of the multi-channel interrogator from 1 Hz to 500 Hz are calculated in the laboratory within 24 hours, which is shown below. The temperature range is from 16 to 27. We can find that the noise level difference between every 2 channels are less than 2.6 dB. The noise level fluctuation of all channels are less than 1.4 dB over 22 hours. Then we carried out field tests, a comparative test between the fiber optic seismometers and the smart solar geophysical using a controllable source vehicle was conducted in Baiyun mining area in Bochkova, in the China. The experimental results show that fiber-optic seismometer clearly records the source vehicle at different locations and different amplitude signals. Take the fiber-optic seismometers at channel 6, for example. Optical fiber seismometer and smartphone have similar spectral response, high amplitude consistency, and the correlation coefficients of the recorded seismic waves reached 0.99. In conclusion, we have implemented broadband fiber optic seismometer system, and field tests proved that the proposed system may be expected to be applied in broadband oil and gas exploration and seismic monitoring. Thank you for attention. Thank you.
Thank you very much.
Thank you.
These questions, any questions? Raise your hand or use chat.
And unfortunately, our conference comes to an end. We do hope we made it interesting for you and see you at OR 2022, 2 years later in Perm, in Western Urals, in Russia. Have a great research, dear colleagues. Goodbye.